Hey guys, welcome to Physical Geography. This video is about convergent and transform boundaries. We've been talking about plate tectonics and specifically about plate boundaries and what happens there. In this one, we're going to look at the two types of boundaries called convergent and transform. Picture here, you see Mount Fuji in the background, which is a product of a converging boundary. So as a background, remember we have three types of boundaries. We have converging boundaries, which come together. We have diverging boundaries where they're moving apart. Then we have transform boundaries where they're not going together or apart, but just sliding past each other like this. There's a lot of friction. So I thought I'd start with transform boundaries because it's a little shorter, so I don't want to leave it to the end. I just do it right off the bat. Transform boundaries. When we talk about transform boundaries, we want to make sure we understand right off the bat that the word transform here is not used in the sense of transforming the earth. It's not saying that we're looking for mountains or volcanoes or something else that's transformed into that. I used to think that a long time ago, and I was looking the book of where's the transformation, what's being formed, and the answer is that's not what it is. What it really is the transformation of the direction, meaning the plates slide past each other like this, and they can slide this way, but then they can later on some other time slide the other way. So the symbol for a transform boundary is two arrows going in opposite directions, not toward each other like this, but just past each other like this. And so that's exactly what plates are doing in a transform boundary. They're sliding past each other. And so you're not going to get any big mountains or any giant volcanoes, but you will get lots and lots of earthquakes. So there's no colliding, no spreading, but lots of earthquakes, lots of friction. And a lot of these transform boundaries are under the ocean, similar to diverging boundaries under the ocean in many cases. But a good example of one that comes on land is in California, the San Andreas Fault, this giant fault or crack that moves through California and it slips like this. And you can see that all the way down in California from San Francisco all the way down. So here you can see it up close. You can see there's this big crack there, the San Andreas Fault. And on the left, you can see that fault goes straight down through California all the way to Mexico. So from transform boundaries, we can move to convergent boundaries. Convergent boundaries is a big category. And within convergent boundaries, there's then three subtypes. There's ocean-ocean, ocean-continent, and continent-continent. Three different subtypes which have three different results. And you can get a preview of what's going to happen in each one. Basically, you can see in the first picture, A at the top, you've got an ocean plate, meaning it has ocean on top of it, and a continental plate, meaning there's no ocean on top, it's just land. To preview the second one, ocean-ocean, it's almost the same thing, except there's no continent involved. And then there's this third possibility, which is totally different, which is a continent-continent collision. And that's where two plates collide and nothing is subducting. Nothing goes underneath anything else. Instead, they both go up. They both push upwards. And you're going to get the biggest, most majestic mountains in the world this way, the Himalayas. So that's a little preview of all three types. Let's go take a closer look and go through it carefully, step by step. So subduction is the action of one plate going down under the edge of the other plate and then sinking into the mantle below. So in this picture here, we would say that Pacific plate is subducting underneath the Eurasian plate. Sub means under, and then duct is to lead along, like air ducts lead air out. So it's headed or leading down underneath this other plate over here. If you remember from the diverging boundaries video, we called this area where the two plates meet the spreading zone. And this is sort of the opposite. This is the subduction zone. So you only have subduction zones at convergent boundaries, and actually only in the first two types of convergent boundaries. That third type, continent-continent, there's no subduction zone. So you might ask, which plate subducts? How do we know which one's going to go underneath? And the answer is that if you're in the ocean, then the heavier plate always subducts underneath. And if it's ocean continent, then the ocean plate is always the one that goes underneath the continent. You never have a continental plate go under the ocean plate. And a very interesting pattern that you can see is that wherever you have a subduction zone like this, and you see the two plates coming together, you're going to get your trench right along the beginning of the subduction zone right here. Two plates come together, and right where they meet, basically this plate and this plate are meeting. These are big, heavy rocks. They're very jagged. And they're downwarping. They're pulling each other down like this. And so you get that crack there. That's a trench. Those are the deepest places in the world, the ocean trench. Okay, so you get a trench along the beginning of the subduction zone where the plates first meet. But then the subduction keeps continuing down, and then it starts to bubble up over here, some distance away from the trench, and then you'll have this set of islands, or if it's a ocean continent boundary, a set of mountains there. So that gives us a nice rule of thumb. Wherever you see a volcanic arc made by subduction in the middle of the ocean or on land, there's always a trench somewhere running parallel nearby. So here's the volcanic arc or the mountain chain on the coast, and there's always a trench somewhere nearby. How far it is away is a function of the angle at which it subducts and other factors. So let's slow it down and look at exactly what happens when these two plates come together. So here comes the lithospheric plate on one side. It's going down underneath the other lithospheric plate on the other side. And the lithosphere is headed down into the asthenosphere, which we know is very, very hot. It's semi-plastic or semi-squishy because it's so hot. That's where magma comes from. So this lithospheric plate is going to get very hot. It's going to start melting. All kind of chemical reactions taking place when it's melting. And also water is getting down in there too, because little bits of water are getting into this crack here, and they're bubbling up too. So all this pressure is developing down deep. And you can see these little red dots. The pressure and the magma are then burbling up because of that heat from down below. And that's pressing upwards and then causing this chain of volcanoes to form. And just to be clear, the volcanoes don't have to be islands. They can be underwater. They might spend a long period underwater before they eventually erupt high enough to get out of the water. So you have lots of underwater mountain chains that are arcs too. You have underwater arcs of volcanoes along convergent boundaries. And if you watch the diverging boundary video, you know that at a diverging boundary, plates are moving apart. And when they move apart, that means that they're creating new Earth because new magma is coming in the middle and then coming out as lava. And new Earth is sort of being born there, coming out onto the crust, or adding crust that wasn't there before. So there has to be an economy of crust. You're going to lose crust somewhere else, and this is where you lose it. So you gain new Earth along the mid-ocean ridges as that new crust is born, and you lose it here when the lithosphere and the crust on top goes down and is recycled, so to speak, down into the Earth, and some of that bubbles up and forms volcanoes here. So when we talk about ocean trenches, we're always going to be talking about an area where there's subduction going on. And way out here in the middle of the Pacific Ocean is one of those areas. You have the Mariana Trench, which is alongside the Marianas Islands, which are owned by the United States. We have Guam and Saipan, a bunch of islands out there. Guam has a military base. And the very, very deepest place in the world that we know of is the Challenger Deep. That is a place, a specific spot within the Mariana Trench. You can see it on the map on the right. This is a bathymetric map showing the ocean floor. And towards the bottom, towards the south end of the Marianas Trench is the Challenger Deep. It's 7 miles deep. So Mount Everest's height can fit inside the Challenger Deep with water to spare on top. People have gone down to the bottom of the Challenger Deep. James Cameron, the Titanic director, and some other people have taken submersibles down there. So people have gotten down there, but it's just one example of a place that before had been unexplored. And a specific example of a place that's created where you have a converging boundary, specifically of a ocean-ocean boundary, is Japan. That's the one used in the diagram here. So here comes the Pacific plate on one side, the Eurasian plate on the other side, and then the country of Japan is a set of volcanic islands that basically popped out of the water at some point in geologic time. That's what it is. It's a bunch of volcanoes. And so you can see on the right, Japan is this elongated island chain that just follows that boundary. Here's the boundary on the left, up and down. The red line is the converging boundary. And then you can see Japan just follows that. And there's a trench right offshore, right over here, right off the coast of Japan. This is what makes Japan such a dangerous place to be, because earthquakes form along these boundaries. And you can see when you're sitting right on the boundary, then any kind of earthquake has a serious effect on you because you're right there, very close to the hypocenter, the energy center of the earthquake. And those underwater earthquakes, they then throw up the ocean and push this gigantic whole ocean wave along, and that's called a tsunami. And so tsunamis are forming right off the coast of Japan, a very dangerous place to be. Here's a picture of some workers at a beer factory in Japan handling all the aftermath of an earthquake. And 75% of Japan is volcanic mountains. So it does get lots and lots of tsunamis and earthquakes. The picture in the opening slide from this video was of Tokyo, and specifically in the background is Mount Fuji. So Mount Fuji is a volcano that formed from a converging boundary, from an ocean-ocean boundary, part of the volcanoes that formed Japan. And it's one of three holy mountains within the Shinto religion. The Shinto religion is specific to Japan. It's just about the relationship between Japanese people and these sort of nature deities. So Mount Fuji is a holy mountain, and it overlooks Tokyo. Another place we can see an ocean-ocean boundary is along the Caribbean islands here. See this huge trench that runs along here? See the Puerto Rico Trench? And this map is skewed. It's actually turned 90 degrees to the right. So north is on the right and south is on the left. And the reason they do that is so they can fit the islands better into the frame. And what you can see is that you have Cuba up here. This is actually Florida. It's part of the United States. Hispaniola, which is Dominican Republic and Haiti, Puerto Rico, and then the Virgin Islands over here. And they're all following the same volcanic arc, the same chain of islands, all created by volcanoes along this subducting zone, along this converging boundary. And this is an ocean-ocean boundary. And if someone were to ask you which one of these plates, the Caribbean plate or the North American plate, is the one that's subducting, you could think about how would I figure that out, right? And so if you look at it, remember we said that there's always going to be a trench before the islands, So that means that we can see the trench on this side. Here's the Puerto Rico Trench. And that means that it must be this plate over here, the North American plate, must be going over this way underneath the Caribbean plate because the trench comes first. And then that means the North American plate would be down under the Caribbean plate and then coming up on the other side as the islands that make Puerto Rico, Hispaniola, Cuba, all those Caribbean islands. And to give an example of an ocean continent boundary, we have the Pacific Ocean. And we have specifically the Nazca Plate, which is off the coast of South America. And that plate subducts underneath the continent, which is South America. And then it bubbles up and gives us the Andes Mountains here. So the Nazca Plate subducts under South American plate, and the Andes Mountains run all the way from the top of South America all the way to the bottom. It's the longest mountain chain on land in the world. And sure enough, there's the Peru-Chile Trench right offshore, just what we said it would be. So that helps us to understand the major system of converging boundaries, which is called the Ring of Fire. The Ring of Fire is a system, sort of like a horseshoe shape, kind of a lazy horseshoe, that's all converging boundaries, and it's predominantly found around the edges of the Pacific Plate and then its neighbors. So it's all around the edges of the Pacific Ocean. And on the western side of the Ring of Fire, you see all these islands like Japan, the Philippines, Indonesia, etc., New Zealand. Those are mostly ocean-ocean boundaries. So you have all these islands that are created, mostly. And then on the eastern side of the Ring of Fire, it's mostly ocean continent boundaries, where the ocean plate is subducting and giving us the mountains all through Mexico and Central America and South America, like the Peru-Chile Trench we said offshore of the Andes Mountains that we just talked about in South America. And here on this map, you can see the Andes going all the way down to the bottom of South America. What this map is showing you is volcanoes, because the Ring of Fire, this big system, this big sort of horseshoe, lazy horseshoe shape, is the location of 90% of the world's earthquakes and 75% of the world's volcanoes. So the vast majority of earthquakes and volcanoes are somewhere on this Pacific Ring of Fire that's formed around the edges of the Pacific Ocean, where the Pacific Plate and other plates meet their neighbors. And just to be clear, we didn't say that all volcanoes are on the Ring of Fire. We didn't say that all earthquakes are on the Ring of Fire, because there's still a lot of volcanoes in other places. Remember, we said that diverging boundaries can create volcanoes too, but not as many as converging boundaries. And there's also earthquakes along diverging boundaries and even transform boundaries too, but not as many as the Ring of Fire. You may be wondering, what is this dot in the middle? This is Hawaii in the middle, and that's made of volcanoes too. That's an arc of volcanoes, but that's a special case. It's not really part of a converging boundary. That is a hotspot underneath of Hawaii. Hawaii is in a special place. That's another lesson about hotspots. Hotspots are sort of a unique case where they're not formed along boundaries, but a hotspot volcano is formed where a blob of magma gets under the earth, all isolated by itself, and then creates volcanoes above it. So to zoom out to the big picture, there's two major systems of plate boundaries. And again, not all plate boundaries are part of these two systems, but it encompasses a lot. So on the left, you have the Ring of Fire, which is the converging boundaries around the edge of the Pacific Plate and its neighbors. Because they're converging, you're going to get lots of trenches, lots of subduction zones, lots of volcanic arcs, lots of volcanic mountains along the coast, like the Andes. And on the right, you have the mid-ocean ridge system from another video, from the video about diverging boundaries, which is mostly underwater and then pops out onto land at Iceland and East Africa. And that's where you have rift valleys, ridges, underwater volcanoes, and some on land too, hydrothermal vents under the ocean, things like that. So both of these two systems produce volcanoes and earthquakes, but the Ring of Fire has many more volcanoes than the mid-ocean ridge system. And another big picture look, when we talked about the diverging boundaries out in the middle of the ocean, we said that new Earth was born there in the spreading zone. Lava comes out for the first time from the asthenosphere, and then it's going to ride the conveyor belt outwards. And eventually, we're talking about like tens of thousands of years later, it's going to subduct. When it finally gets out here, it's going to subduct downwards and go back into the asthenosphere and be recycled. So Earth is born and Earth is recycled in this continuous cycle from the spreading zones at diverging boundaries all the way out to the subduction zones at converging boundaries. So that leaves us with our last type of converging boundaries. This one's a little bit different. It's doing its own thing. So we got to keep our eyes peeled here, and we got to pay close attention to the details because it can be very confusing if you miss one of the aspects of it. It's not that confusing overall once you understand it, but if you miss a piece, it can throw you off. So these are the continent-continent boundaries. So there's no ocean involved. You see the top one, we had ocean continent, there was an ocean there. The middle one, B, we had ocean, ocean. But the bottom one, C, we have two continental plates coming together, and there's no ocean involved. So what happens? One of the easiest ways to understand how these boundaries work in continent-continent boundaries is by an example. We look at India, for example. If we go back 71 million years ago, India, which is shaped roughly like a pizza, like a triangular shape, was out in the middle of the Indian Ocean. And it was a subcontinent all by itself out there, unique wildlife species, etc. And slowly, it rode along on this plate all the way over 71 million years towards Asia, to the point where eventually it collided in what they call sutured or stuck itself onto Asia. They also call that accretion, or it accreted onto Asia. So India stuck itself onto Asia, and as it did that, they collided. So we have a continent-continent collision, two pieces of land. But what we have to remember is before they met, before they collided, it was an ocean-continent boundary because there was a bunch of ocean between India and Asia. So there's all this ocean plate that subducted under Asia first before India finally came up behind and then finally sutured itself or stuck itself on. So if we remember that, that helps us to understand what's going on in these diagrams here. Notice that here's the Indian plate right here, right? India over here. Here's the Asian plate. And this is going this way. And what this is showing you down here, it says subducted ancient Indian oceanic lithosphere, meaning this is all of the plate that was under the water between India and Asia for 71 million years. Where'd it go? It went underneath Asia. It's subducted. All that plate subducted underneath. And they press together. And if you can see up here, what happens is that they squeeze into each other and everything goes together into the mountains. So in other words, all this material from India, this gets kind of shoved in there in the middle. Behind it was Tibet, also shoved up there. All that gets shoved into the mix too. So you have all this continent and continent material together. And that helps to explain why these are the highest, most majestic mountains in the world because you have sort of two continents worth of materials that are both combining into the same set of mountains. Not to mention the fact that you had 71 million years of subduction before that. And you could even remember, too, that there was all of this earth in between here, little islands, little things that might have been in here on the ocean floor that during the subduction got bulldozed into that mix and just shoved up into the earth material that contributes to the Himalayas mountains. So what you see with all these little arrows and slices here is many, 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 many millions of years worth of accretion, meaning adding on territory, adding on earth, stuck onto Asia again and again and again and again and again. So this is what you get, the Himalayas, a product of a continent-continent collision. And the Himalayas is both the range of mountains and then even a bigger system of mountains. It goes all the way through multiple countries up here in South Asia where it meets China. And the Himalayas contain the highest mountains in the world. The highest mountain of all is Mount Everest in this picture. And then also K2 is number 2, and a whole bunch of the other highest mountains in the world in the Himalayas. And what you can see in this picture is that here's the Himalayas here, the brown at the top of India there. But as you keep going farther north, you get to China and specifically the region known as Tibet, which is the world's highest and largest plateau. Tibet is known as the rooftop of the world. Many of Asia's rivers flow down from there. But in addition to the Himalayas, which are a continent-continent collision today, we have a continent-continent collision of the past that's very important. And this is what formed the Appalachian Mountains, for example, on the east coast of the United States, including Virginia. So the Appalachian Mountains were formed during the time of Pangaea. That's when all the continents were together. And specifically when North America was right adjacent to Africa. And so you could walk from Virginia to Africa during this time. You could walk from Virginia to somewhere around what's now Senegal or Mauritania. And so in this picture here, you can see that it's showing you on the right is Africa and on the left is Virginia. And it's showing you the major geological regions of Virginia, the coastal plain that's flat, the Piedmont, like the foothills, and then the Blue Ridge mountains, and then the Valley and Ridge all the way out. But this is showing you after the mountains were formed. So now it's showing you in this picture, there's all this space between Africa and Virginia. But here you can see there was no space. They were right up against each other. So the Atlas Mountains of Africa over here, which are still there, like in Morocco, etc., they were formed together by pressing up against the Appalachian Mountains within North America that run through Virginia, through Pennsylvania, through North Carolina, South Carolina, all up and down the eastern side of the United States. And then after they formed together, those two sets of mountains, those two continents, they then moved apart along this diverging boundary that you see in the middle later. So first it was a converging boundary, a continent-continent boundary, similar to the Himalayas. And then once those mountains formed, then later it became a diverging boundary when Pangaea split apart. And we said that continent-continent boundaries create the highest, most majestic mountains, like the Himalayas. And you may be saying, well, the Appalachian Mountains don't look that big. They're not like the biggest mountains in the world, the most majestic. And that's true. That's because they're extremely old. And when they were first created, they really were bigger than the Himalayas. But they're much older than the Himalayas. And so they've been worn down over time. So they're just kind of like large hills. But these mountains were once higher than the Himalayas. You can also see older mountains because they're more smooth, whereas younger mountains tend to be much more jagged. And if you're not familiar with the Appalachian Mountains, they go by many names in many places. So if we look at Virginia here on the map, we see there's the Blue Ridge, that's part of the Appalachians, Alleghenies, which go up through Pennsylvania. If you go up to, for example, New Hampshire and Vermont, you've got the White Mountains and the Green Mountains, the Catskills and the Adirondacks in New York State, the Smoky Mountains in Tennessee. These are all like subsets of the Appalachian Mountains. And the Shenandoah Valley is the valley between the Allegheny Mountains and the Blue Ridge on the other side. They make that V shape and they come together. And that in the middle there is the Shenandoah Valley. So as we look at transform and convergent boundaries, we can see now the Earth is very dynamic. It's always changing and new landforms can be built. And these are some of the ways that nature is always shaping the Earth.